we're going to introduce the concept of sigma fields. This concept is also introduced to help build the foundation for probability measure. A random experiment refers to an experiment whose exact outcome cannot be determined in advance, other than knowing that it must be one of a set of possible outcomes. The set consisting of all these possible outcomes is called the sample space. If 2 dice are rolled and the sum of the numbers facing up is calculated, the sample space is the set S equals 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 students each randomly pick an integer from the first 52 positive integers. What we care about is whether at least 2 of the 6 integers are the same, represented by M, or if they are all different, represented by D. So, the sample space is the set S equals M, D. Suppose that a fair coin is tossed repeatedly at random until we get the first head. If we let X be the number of flips needed, then the sample space is the set S equals 1, 2, 3 to infinity, which contains infinitely many but countable outcomes. To measure someone's body fat percentage, one of the measurements taken is their weight underwater. If we let W be this underwater weight in kilograms, then the sample space can be set as S equals 0, less than W, and less than 7, because we know from past experience that this weight never goes over 7 kilograms. Given a sample space S, suppose A is a subset of S containing a portion of the outcomes in S. Then A is called an event. When the experiment is performed and the resulting outcome belongs to the subset A, we say that event A has occurred. In studying probability, the words set and event are interchangeable. We introduce the concepts of mutually exclusive events and exhaustive events as follows. We say that a collection of events A sub 1, a sub 2 to a sub n are mutually exclusive events when the intersection of a sub I and a sub j is an empty set for I not equals j. In other words, a sub 1, a sub 2 to a sub n are disjoint sets. If the union of all a sub 1, a sub 2 to a sub n equals the entire sample space S, we say that this collection of events are exhaustive events. Saying that the events A sub 1, a sub 2 to a sub n are both mutually exclusive and exhaustive means that the mathematical expressions in the last 2 lines on the screen are satisfied. The 2 equations shown on the screen are De Morgan's laws, which describe the relationships among the sets of complement, intersection, and union. This screen defines the concept of sigma field. Suppose that S is a sample space. We consider a collection F of subsets of S. This collection F is also a set whose elements are subsets of S. In other words, the collection F is a set consisting of subsets of S. If the collection F satisfies the following conditions, we call F a sigma field. The first condition is that F must be a non-empty collection, that is, F cannot be the empty set. The second condition is that F must be closed under complementation, that is, for any element A in F, its complement set a sup C is also an element of F. The third condition is that F must be closed under countable unions, that is, when a sub I are all elements of F, their countable union is also an element of F, as shown in the last mathematical expression. This theorem shows that the collection F is closed under countable intersections. That is, when a sub I are all elements of F, their countable intersection is also an element of F, as shown in the last line of the mathematical expression. Its proof is on the next page. First, according to De Morgan's laws, we obtain the second line of the mathematical expression by applying the second condition of sigma field, namely, that F must be closed under complementation. The complement set of each a sub I is also an element of F, as shown in the third line. Next, by using the third condition that F must be closed under countable union, we deduce that the union of the complements of a sub I is also an element of F. Then, applying the equality in the second line yields the second-to-last mathematical expression. Since the complement of a complement restores the original set, applying the second condition once more proves that their countable intersection is indeed an element of F, which completes the proof. This example presents three collections F that constitute sigma fields. That is, they satisfy the three conditions in the definition, which should be straightforward to verify. Suppose that a collection C is a set consisting of subsets of S, which, of course, does not necessarily constitute a sigma field. The goal is to extend the collection C so that the enlarged collection forms a sigma field. This theorem illustrates how to construct the minimal enlarged collection, namely, by considering the intersection of all sigma fields containing C, as shown in the second line. The theorem proves that this intersection is indeed a sigma field. This screen illustrates that the sigma field constructed on the previous page is indeed the minimal sigma field containing C. The significance of this is that although C itself does not constitute a sigma field, we can add elements to C so that the enlarged collection forms a sigma field. Naturally, the fewer elements added, the better. Therefore, the minimal case is achieved by taking the intersection of all sigma fields containing C. In this context, we also say that this intersected sigma field is generated by C. Suppose C sub 0 is the collection of all intervals on the real line. Then C sub 0 does not necessarily constitute a sigma field. In this case, the minimal sigma field containing C sub 0 is called the Borel sigma field. This is a special type of sigma field that is considered specifically on the real line. This theorem shows that to generate the Borel sigma field, the underlying collection does not necessarily have to be C sub 0. That is, it is not required to use all intervals to generate the Borel sigma field. For instance, C sub 3 on the screen, which consists of all closed intervals, can also generate the exact same Borel sigma field. This screen lists 5 different collections, all of which generate the same Borel sigma field. Continuing from the previous theorem, this screen lists another 3 different collections of sets that also generate the exact same Borel sigma field. Simply put, we have 8 distinct collections that all generate the same Borel sigma field, where the endpoints of the intervals in the underlying collections can be arbitrary real numbers. The last 3 lines of this theorem state that we can reduce these 8 underlying collections and still generate the same Borel sigma field. This reduction is achieved simply by replacing the real endpoints with rational numbers. Such a reduction of the collections relies on the denseness of real numbers. The denseness of real numbers is a fundamental theorem showing that any real number can be approximated by rational numbers. For instance, there exist rational numbers that lie extremely close to the irrational number square root of 2, as close to square root of 2 as one desires. This screen illustrates that a Borel sigma field can be defined on any n-dimensional Euclidean space. Its underlying collection of sets consists of all n-dimensional intervals. A 2-dimensional interval refers to a rectangle, while a 3-dimensional interval refers to a rectangular cuboid. Extending this by analogy, the concept of an n-dimensional interval is straightforward to understand. Therefore, as long as the underlying collection C sub 0 is composed of all n-dimensional intervals, the minimal sigma field containing C sub 0 is called the Borel sigma field.